Some traffic in my office hours. There are several things I think I should mention. Okay. First, Reynolds number. Okay, so this is in momentum transport. This is probably one of the most important dimensions numbers we'll ever use. Okay. Now, of course, we have two equations here. And Reynolds number equals to blah, 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 and that, okay? And Reynolds number equals to that. So, which one you should use, okay? As you can see here, this is what? That's the general definition of Reynolds number, okay? So in general, it should be density times a characteristic velocity, and then times a characteristic length divided by the viscosity. General definition. So that means for a specific problem, you have to choose the characteristic velocity and the characteristic length to get a more specific calculation of the Reynolds number for a certain problem. So after you've done that for the forming film problem, and this is the Reynolds number for this problem. Okay? All right? Let's clear this up. Now, of course, you may wonder, how did we choose these numbers? So I mentioned here that once we finish the example of cube flow, you'll know why this is what it is. Okay? Okay? All right. So this is one. Now, the other thing I want to mention is in problem number 2 about the falling film problem. Of course, you know now it's vertical. Beta is 0, and you're given the Reynolds number, okay? Now, of course, what you should try to do is look at the equation we have for the whatever calculation you're asked to do, and look at what is known, okay? You can look up the density, you can look up G, you can look up viscosity, and then look at what's given. Okay, you're given the Reynolds number and temperature, right? So, and use the known variables or numbers to try to sort of calculate the unknown parameters that you need to do that calculation. Okay, so don't tell me that, okay, I need this, it's not given, what should I do? Well, you're engineers, right? You should know a little derivation. Okay, all right, so and also, again, let me emphasize this. Try to study the notes and understand the notes before you work on the homework problem, okay? Now, if you look at the homework problem, you don't know where to start, that means your understanding of the notes is off. Very simple, okay? Okay, so, of course, if you have a hard time understanding, you should come to my office hour and the PA's office hour, okay? So, again, this is not easy. I mean, transport is not easy, okay? So you may think QP is not easy. Well, transport, these concepts, they're not easy to understand, okay? So you really need to spend enough time on this, okay? If you keep putting this off, well, pretty soon you'll find out it's too late to catch up, okay? So, all right? So, last time we talked about Newton's law in 3D. Okay, so mainly we used the rectangle component system to identify all the 9 components of the stress tensor. Okay, so 9 components. Now, someone asked me to draw these components in the cylindrical and spherical coordinate system. So just to remind you, cylindrical, okay, X, Y, Z, that's R, that's theta. So these are sort of inside the XY planes, different XY planes. Okay, so spherical, this R is a little different. So this R is from the origin to any direction. That's all. Okay, theta and phi, 3 directions. I did draw these directions of shear stress. I mean, all 9 components. Okay, So this is on campus, okay, in that folder called handouts, okay. So cylindrical reference coordinate system, so R direction, theta direction. Imagine that R here, theta that direction, Z is the same, okay. So all the 9 components, obviously, you can see this is the R direction. This is sort of like a control line, okay. In the R direction, you get the R, right? So theta direction, obviously, it's that direction. You get an arc because theta is the angle. When you vary theta, you get an arc instead of a straight line, okay? And Z, of course, that straight line, okay? So look at these surfaces. Obviously, this is the surface with a normal direction in the which direction? R direction, right? Okay. So this is a surface. You can see the normal direction is in the R direction. See, that's the arc, okay? All right? So, of course, then if tau R is larger than 0, you should point to the negative R direction, see? Okay? All right? Going in. Dashed line, going in, okay? All right? So, of course, R theta, negative theta, RZ, negative Z, okay? Now the theta surface, it's this back surface, okay? Right? So that's the theta direction. So that's the surface with a positive theta direction of the normal direction. This is negative, okay? So couldn't find a space to draw there, so I took it out and put it here, okay? So that's that back surface. So theta direction, of course, theta theta, theta R, theta Z, okay? Z direction, that's easy, so because that's the Z, so that's positive Z direction, normal direction. So ZZ, ZR, Z. Okay? All right? So spherical. This is a little hard because, see, that's R direction, okay? You vary R, you get the R. And the line element in the theta direction. So when you vary theta, that's what you get, an arc, okay? When you vary phi, that's that arc, you get that, okay? Obviously, R direction, theta direction, and phi direction, like that, okay? So R, theta, and phi, okay? So obviously, this is the surface with the normal direction in the R direction, okay? So R theta, R phi. Okay, so this is the surface with the normal direction in the theta direction. Okay, so normal direction, that direction, theta direction, so forth. Theta theta, theta R, and theta phi. Okay, so the surface with the phi direction, that's again that back surface. Okay, this, that. So again, I don't want to draw it there, so I took it out and put it here, the back surface. Okay, so. Phi direction, okay? Phi R, negative R direction, negative theta direction, okay? So these are the components of the stress tensor in various coordinate systems. This is on campus, okay? All right? So that, then, we're looking at the flow through a circular tube problem. So again, this is our practice of using the shell balance method to solve a momentum transport problem, okay? So if you lost track of sort of the thought process, okay? So basically, we're in momentum transport, right? So first two lectures, we introduced some concepts, and we said we're going to use the shell balance method to solve problems in momentum transport. And then we talked about falling film, right? Rectangular. So tube flow, cylindrical coordinate system, okay? So, all right, so of course, blood flow, that's the reason for us to consider this pressure driven. So that means P is function Z, long tube, okay? L is much larger, so that we can consider this as a fully developed flow problem, okay? So that means fully developed. That simply means velocity does not depend on z anymore. Okay, z direction, the velocity profile doesn't change anymore. It's not a function of z, only a function of rho. It's not a function of theta because of axis symmetry, okay? So how long does it take to become fully developed? No. That's the length you need. Okay, this doesn't matter if you don't want to care, okay, because we're considering a fully developed flow anyway. So if you don't want to care how long it takes, it's okay. All right. So, all right. So that's where we ended. The radius of the tube r, coordinate system, r and z. Of course, theta is that direction. Okay. All right. So axis symmetry. So theta won't come into play a lot here, okay? So, all right, so we'll set up the problem. Of course, once we know all that is known, to use the shell balance method, what's the first step? Control volume, right? Okay, because the method says in any control volume, changes overall, right? So you have to have a control volume. How do you select the control volume? So you have to select a volumetric element, right? Okay, that's small enough that's representative of any location in the flow field, okay? So in here, because of axis symmetry, okay? So that means, how do we select? Well, in general, when you select the volumetric element in the cylindrical coordinate system, and by the way, the name of the title or the name of this file is stress component cylindrical length program. Okay, so in general, in a cylindrical coordinate system, when you select a volumetric element, small volumetric element, this is what we should have, okay? ER, RB theta, okay? And DZ, okay? Very small. In general, this is how we should do it. However, for this tube flow problem, we know we have what? Axis symmetry, which means things will not change in the theta direction. So as a result, we can just what? Yeah, well, you can say ignore that dimension or use the full circle. Either way, it doesn't matter, okay? So it's like in that folding film problem, okay? One dimension doesn't matter, you can just draw that, the other two, okay? So in here, since it does not depend on theta, so that means the R and Z direction, that's our major sort of concern, okay? Yeah, let me draw, start a new one here. Let me draw a new diagram, okay? So the volumetric element, since theta direction doesn't matter, okay? Only delta R and Z. So what we can do is select a ring of fluid from this tube flow. Okay, so that means we can cut out a cylindrical ring from this fluid as our control volume. Okay, so any R location, at an arbitrary R location, of course, you let R vary from R to R plus delta R, okay? And you get a ring, right? We cut it out. That's our control volume. So let me draw it here. and the delta z, of course, okay? So that means the length here is delta z, and this is delta r. So the radius here is r. Obviously, outside here, that's r plus delta r, okay? All right, you see what I'm trying to do, right? So this is a cylindrical ring cut out from that fluid flow, okay? So the thickness is delta r, this is delta z. That's our control volume. That's all because theta doesn't matter, okay? We can do this, okay? All right? So, of course, then we need to do what? We need to do the moment balance in this control volume, or another way to say this is to use the shell balance method to look at the momentum conservation in this volumetric element, just like what we did in the following film problem, right? Okay, so change. Emission steady state. Oh, well, okay. So add this at the beginning. Indeed, we're looking at the steady state. Okay, so we're just starting, so we don't want to look at any problem that's changing over time. All right, so of course, that simply means, just like before, you know, at steady state, we don't really expect any change in any control, okay, in terms of momentum, okay? So there's no change, so all we need to look at is the in, out, generation, and consumption, just like before, okay? So, all right, so the amount of momentum that's flowing into this volume and out, okay? So how many surfaces are we looking at here? So we need to look at the in and out on all the surfaces, right? To figure that out, of course, to make sure that we don't miss any, you need to know how many surfaces we're looking at. Okay, so how many surfaces are we looking at? 4, right? Okay. So inner cylindrical surface, outer cylindrical surface, top ring, and the bottom ring here, right? Okay? So just to, so basically this is what we have. So inside here, all right? So 4 surfaces. Now there are 2 surfaces where the momentum is now flowing in or out, right? Which 2? The inner cylindrical surface and the outer one, right? That's because we have a tube flow in the z direction. You look at the velocities on these surfaces. So the velocity on the outer cylindrical surface and the inner cylindrical surface, on these surfaces, the velocity is tangential to the surface, right? So of course, that means no mass is going in or out on those surfaces, and there's no contribution to the momentum flowing in or out, okay? So that leaves us with 2 surfaces, the top and the bottom here, okay? So do we have momentum flowing in or out there? Of course, okay? Because you look at here, so on these surfaces, on this surface, the velocity is what? Perpendicular to that surface. Obviously, there is momentum flowing in, right? By convection, okay? So, how do you calculate the momentum that's flowing in on the top surface? So, the amount of momentum flowing in. How do you calculate? Okay, so momentum flux times area. Momentum flux is rho v and v. Okay, so on the top surface, rho, we know the velocity is in the z direction. So on the top surface, this velocity is where? At z, right? So basically, that's where z is, okay? So of course here would be z plus delta z, okay? So that times v sub z and z. So in this case, the velocity is perpendicular to the surface, so that's how you calculate the momentum flux, right? Okay? So flux times area. What's the area of the string? Very easy, right? So pi times r plus delta r squared minus pi r squared. That's that area, right? You can just write that area as 2 pi r delta r. Why? That's because if you calculate that area difference, okay, what I just mentioned, pi times r plus delta r squared minus pi r squared, you will have 2 pi r delta r plus what? Delta r squared, okay? That delta r squared is a higher order term compared with delta r. So that one is neglected, okay? Which is why I kept emphasizing what? This is a small volumetric area, which means delta r, delta z, they're all very small, okay? Okay, when it's small, you can ignore the higher order terms. Just use that as an approximation for the surface area of the string, not ring. Well, it is surface. Okay, all right. Okay, so that's the amount that's flowing in. Now the amount of momentum flowing out. We're looking at this surface here, okay? So rho velocity at z plus delta z, okay? Bottom surface. So this times velocity, again, at the same location, will give us the flux. So times area again, that's the amount that's flowing out. So again, we're at what? Steady state and fully developed. Because it's a constant cross-section. Just like the falling film problem. There's no change in the velocity from z to z plus delta c, okay, fully developed. So that means, well, these two are equal, okay? In is equal to out, so they cancel, okay? In the shell balance method, okay? So this is the same as before. Now, of course, what's left is what? Generation and consumption, okay? So in this case, of course, again, you always try to start with what? Gravity, okay? And look at whether gravity has any contribution to this, to the generation and consumption. So in this case, if we assume the gravity is, again, pointing straight down, does gravity contribute or generate momentum? In the z direction, of course. Why not? Because, see, force is acting on this, on the mass here, on the fluid, okay? So we know force generates momentum, right? Okay, all right, and the direction of the force is right in the direction of the component of the momentum we're considering, the z component of the momentum, right? Okay, so when you look at momentum generation or consumption, basically you need to look at all the forces acting on the volumetric element, right? So, and this is the momentum generated by the gravity. Now, how do we calculate the amount of momentum generated by gravity? Well, you know what? Force is equal to momentum per time, right? Okay, that's exactly what we're looking for, because what? See, all these represent momentum per time, okay? So if you can find the force, then you found momentum generated per time, okay? So basically we need to what? Find what? Well, the gravitational force. So in this case it's rho times volume. So 2 pi r delta r, that's the area of the ring times delta z. Of course, that will give us the volume of this volumetric element that we chose earlier. Volume times what? G. So mass times G, that's the gravitational force, which is momentum per second. That's also momentum generated per second by the gravity, okay? So that's a body force, which means the force is on every molecule, and that's it, right? So we don't really have other body forces here to consider. So once you consider the body force, the gravity, you need to consider the contact force, okay? The contact force acts on where? Surfaces, okay? So I have 4 surfaces to consider, okay? All right? So on the top surface, on the top surface, let's consider that one first, okay? What kind of surface forces do we have here? Or how many? Well, we know there should be forces there, right? Okay. So we just learned Newton's law in 3D, okay? So now we should have 3 components of the stress tensor here, right? So basically force could be in all directions. Due to what? Due to the momentum transport by molecular interactions, okay? Basically due to what? Viscosity, okay? We could have 3 components. However, okay, when you look at those components, so first of all, that's a surface what? With a normal direction in the z or negative z direction. So top one is the negative z direction, right? We may have tau zr, tau z theta, and tau z, right? So you look at tau zz, we mentioned what? Fully developed, right? So that means dz will not change in the z direction anymore. So that means this derivative is what? 0, right? Okay? Okay, so that means this component is 0, okay? And tau zr here. There's no VR. Okay? All right? There is Vz, and Vz may change in the r direction, right? Vz, and the velocity may change in the r direction. So this one may not be 0, okay? Then you look at tau z theta. Partial theta, we have what? Axisymmetry. So things should not change in the theta direction. So, and besides, well, this is 0, right? There is no d theta. So this component is what? 0. Okay? All right? So that means of the three, when we need to consider what? This one, tau ZR, okay? All right, tau ZR is the shear stress acting in which direction? So this shear stress, tau ZR, is pointing in which direction? Either positive R or negative R direction, right? So that means what? This force, this shear stress, does it have any contribution to the momentum generation in the Z direction? No. Okay? All right? So there we go. We showed what? On the top surface, either the force is zero, either the shear stress component is zero, or that component has no contribution to the momentum generation in the Z direction, right? Okay, that surface is gone. Okay, so that means on that surface, no force will generate momentum in the Z direction. Okay, we're considering momentum in the Z direction, so that's gone. Okay, for the same reason, you look at the bottom surface. Oh, I should have. So on the bottom surface, the same reason, okay? We'll be able to show that on this surface, all the components of the stress, they don't have any contribution to the momentum in the Z direction, okay? All right, so two surfaces are gone, okay? That means only the inner and the outer surface, outer cylindrical surface, we need to consider, okay? Now to do that, let me draw a new diagram, basically just to draw part of it, to show you the directions of these stress. So this is like, so I cut a small part out of it, okay? Because this way I can draw the directions of the stresses easier, okay? Rather than there. It's hard to see where things are, okay? All right, so basically this is the inner cylindrical surface and the outer, okay? These are the two surfaces we are considering. So, on these surfaces, okay, the normal direction of the surface is in the R or negative R direction. So this one is the negative R direction. Okay. Again, you have three components, right? Tau RZ, tau R theta, and tau RR. Again, you will find out there are two are zero if you look at the equations in handout number 2, as we just looked at. Okay. You'll find out the only one that's not zero is tau RZ. Okay. All right. So the other two are zero, okay? So on this surface, tau RZ is at which location? What's the coordinate? R, right? That's the inner surface, so that's R. Outer is R plus delta, okay? So that's that tau RZ, all right? So, as mentioned before, if we only write the symbol, before we know whether this tau is positive or negative, we assume it's what? Positive, okay? All right, so this tau RZ, if it's positive, in which direction it points to? Positive or negative Z direction? Positive. You said positive, that's very good. Which means you didn't really have to think for long before you know it's positive. So that means your understanding of the positive definition of this stress is good enough, okay? So all of you should try to be able to do this fast, okay? That's because what? The normal direction of the surface is the negative R direction, okay? If this is positive, of course, it should point to this direction, okay? Why this direction is important? Because you need to know whether it's generating or consuming momentum, okay? All right? So that's the inner surface. Outer surface, I can still draw it, okay? Outer surface, that would be tau RZ at R plus delta R. So that's on the outside there. So on that surface there. The normal direction of that surface is what? Pointing in the R direction, right? Okay, so that means if this is positive, it should point to the negative Z direction. So that means this force here, tau RZ, is like that, okay? It would consume the momentum, okay? Okay, anything else? Any other force we need to consider? We talked about gravity, and we talked about the contact forces, shear stress and normal stress, okay? What else do we have here? Yeah?
Friction?
Friction, good question. So, in the fluid flow, okay, the frictional force basically is what? Is these forces, okay? So the relative movement of these different layers of the fluid, this is caused by that, right? So, anything else? And this is where the difference comes in between this problem and the falling film problem, okay? Yeah?
Is there any pressure?
Yeah, there you go. So this is a pressure-driven flow, okay? So that means when you consider the flow, so pressure is larger on the top and smaller at the bottom, right? So that means at different locations of Z here, pressure will be different. Pressure is basically what? A force, like normal stress, right? Okay. For the pressure, we have to use this diagram again. You look at pressure, as you learned from physics, pressure is everywhere, right? Okay. Pressure is acting on all these surfaces, okay? All right, so first of all, the pressure is acting on the inner cylindrical surface, right? Okay, does that pressure have any contribution to the generation of the momentum in the Z direction? No, okay? And besides, it doesn't have any contribution to any momentum generation because that pressure, you can see, it's in all different directions of the surface, right? So there is that, here, there, so it's in all kind of directions. So they cancel each other, basically, right? And on the outside surface, of course, the pressure is always what? Is always perpendicular to the surface and going into the surface, into the volume, right? So here the pressure would be that, there the pressure would be that, here would be here, okay? So again, this pressure does not have any contribution to the momentum generation in the Z direction because they're all perpendicular to the Z direction, okay? All right? So again, two surfaces are gone. All we need to consider now is the pressure at the top and the pressure at the bottom. So the pressure on the top, pressure at the location of Z, okay? So pressure is always perpendicular to the surface and going into the volume, right? That's how it operates, okay? We're talking about the pressure applied onto the volume, of course, okay? And also at the bottom here. So at the bottom would be P at the location of Z plus delta Z. Okay? Well, that's about it, right? So now, once you figure this out, it's like finish up. It's like you have finished your free body diagram, okay? in either physics or mechanics. Okay, so after that, we just need to look at the generation and the consumption and everything. So that's a generation, right? So this tau RZ will generate momentum. Again, to figure out the momentum per time, we just need to look for the force. So this is stress, is force per area. This stress multiplied by the area of the whole inner cylindrical surface. That will give us the force, right? This one generates, so it's tau RZ at R times the inner surface area, so 2 pi r delta z, right? So it's better to look at this one. Inner cylindrical surface. 2 pi r give you the circumference times delta z will give you the inner surface area, right? So this one generates momentum, and then tau RZ at R plus delta R. So here, the outer cylindrical surface area is 2 pi R plus delta R times delta Z, right? Okay, and the pressure P is acting on this surface, which we know the area is 2 pi R delta R. So, and the top one generates momentum, so it's P at Z times 2 pi R delta R. And the bottom one, oh, what's wrong here? Direction, okay? Pressure is over particular going into the volume. Okay. Sorry about that. Okay, so this one consumes momentum P at Z plus delta Z, same surface area, 2 pi R delta R. Okay? All right, so we're done, right? Change, which is 0, equals to generation plus this, minus that, plus this, minus that. Okay? That's our equation. So we have rho 2 pi R delta Z G plus tau RZ at R 2 pi R delta Z minus tau RZ R plus delta R 2 pi R plus delta R delta Z plus P Z 2 pi R delta R minus P Z plus delta Z 2 pi R delta R equal to 0. Almost there. So the rest of it is the same trick that we've used in the folding film problem. There, when we divided both sides by delta x, right? So here, we divide both sides by delta R and delta Z, okay? So divide both sides with 2 pi R, delta R, and delta Z. Then you let delta R and delta Z go to 0. Again, that's why we use a small volumetric element, okay? Smaller, 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 until it's like a point, okay? So then we get the equation that we can use for all the points in the flow field, okay? Since it's divided by 2 pi R, delta R, and delta Z, so you can see maybe, yeah, this one, okay? So 2 pi r delta z. You can see 2 pi r delta z. At the bottom, we only have what? Delta r left for this minus that, okay? And for p minus this, you can see we divide by 2 pi r delta z. So 2 pi r delta r, we only have what? Delta z here left, okay? So this minus this divided by delta r, this minus this divided by delta z. We let these two go to 0, so we get two derivatives, right? Okay? So then we'll have two derivatives. One more step, just to make this clear. Let's move these two to the right hand side because, you know, right now it's z minus at z plus delta z. We move it to the right hand side. Then we have the p at z plus delta z minus the p at z. What we have is rho ng equals to limit delta r goes to 0 and tau rz. Thus, times this minus tau rz at r times r divided by delta r. Okay? All right? So you can see divided by 2 pi r delta z. Right? So delta z is gone, 2 pi is gone. Delta r, we can't cancel because this r plus delta r, okay? So, and that's why we have that. And the other term is plus limit delta z goes to 0, and we'll have p at z plus delta z minus p at z divided by delta z, right? Okay. So this one will give us dp dz, right? This one will be a little complicated. Basically, see, the value of tau rz times r at r plus dr. You can write this as also like this, right? Tau rz times r at this, right? This number here can be also written like this, right? Okay? The product at this location, that's that. So of course, if we write it like this, it's easier to see. So you can also write this one as tau rz r at r, right? So it's easier to see on the top. So this term, the derivative would be oh, there's something else. I missed something, sorry. 2 pi r, oh yeah. I forgot an r. Okay. So it's divided by 2 pi r delta z, right? So delta z is gone, 2 pi is gone, but this r should be still here, okay? So we put that r out and divided by delta r, so you have d dr r this plus dp dz, right? Correct? Okay, so now we have our equation. So rho g is equal to this, okay? We can move the pressure gradient to the side, and we'll have this, right? So move the pressure gradient to the inside, you can get negative plus rho g, okay? So rho g is constant. So, and then we can write this as negative d p minus rho g and z. Like this, right? See, that's because you can write rho g as d rho g z dz, right? Okay? So you combine the two, you have this negative, negative, that's plus, right? Okay? And we write it like this. That's because this p minus rho gz is defined as the capital P, and we write it like this, capital P dz. So of course, you know, this capital P is equal to p minus rho g and z. Okay? All right. Yes?
What is big P again as opposed to little p?
Big P is equal to that. It's, yeah, it's like, you know, including the gravitational potential into the pressure P. Okay? All right? So, how many of you have taken partial differential equations? A few? Okay, all right. So if you have taken partial differential equations, then you know what we're going to do is a common trick that's used here, okay? You look at the right-hand side. You see what? A function of P, a function of Z, right? Okay? You look at the left-hand side, what do we have? A function of R, okay? So basically, you have a function of R equals to a function of Z all the time, okay? So what does that mean for these two functions? Independent. That's correct. Anything else? How can they become independent? They have to be equal to a constant, right? Otherwise, there's no way for these two to be equal to each other for all these different R's and Z's all the time, okay? There's another way to look at this, a simple way. So let me write it quickly here. If you have AX equal to B of Y all the time, you can differentiate yeah. So partial A, partial Y would be what? 0, right? Since A is equal to B, so that means partial B, partial Y is also 0, right? So that means what? B is a constant, see? You look at this side, you know B is a constant, right? Okay, so that's one way to look at it, yeah?
Would be the partial of B with respect to x.
Oh, no. So this is exactly what I'm trying to do. I want to calculate dA dy, because A is only a function of x, right? You know dA dy is 0, right? So A is equal to B, of course, that. Okay? Yep. All right, so these has to be constants. So that means, well, okay, we know the solution here. This is equal to a constant, okay? That's easy to solve. That means P, capital P is equal to C1 and Z plus another constant. So that's the solution of this simple ODE, right? Boundary conditions for P. Generally, we can measure the pressure the entrance and the exit or the outlet of the blood flow. So we'll know the pressure. So we'll know the pressure there as P0. Since here Z is also equal to 0, so P0 is equal to capital P0 at Z equal to 0. Okay? And at the other end of the tube, this is equal to PL minus rho G and L. And we'll call this P, capital P at L. Okay? So this is nothing. You just need to measure the pressure, and that's it. So then we know the solution. You can use these two boundary conditions to determine these two constants, right? Some algebra, okay? I won't go through that process, okay? So you plug this in, okay? Z equals 0, that is P0, or P0 there, it's this plugged in, solve for C1 and C2, so there you have it, okay? You find out that C1 is P0 minus PL over L, Z plus C2 is P0. Okay? So that's the pressure. And of course, from here, we know this gradient. dPdZ negative is equal to that, of course. Okay? All right. So, between P0 and PL, okay? Which one do you think is larger? If this is a pressure-driven flow, you expect the pressure to be larger at the top or the bottom? Top, right? Otherwise, you cannot drive the flow, okay? So that means this should be larger than that, okay? So this is larger than 0, that means what? The pressure gradient should be negative, okay? Along the Z direction, so. All right, so now we know this constant, okay? So we said earlier that this should be a constant. So now we know this constant. Basically, it's the negative gradient of the pressure. So then we can solve for what? For the stress, okay? Because this should be equal to the same constant. So we'll have this equal to P0 minus PL over L. All right, another differential equation to solve. How do we solve this one? Integration, right? So multiply both sides by R, okay? And integrate once. And you have 0 L R squared plus a constant, right? So you multiply both sides by R. So on the left, you just have the differentiation left. So this side is this times R. You integrate. You get this on the left. Right-hand side, you get R squared over 2 plus a constant, right? What's next? Well, you divide both sides by R, you have the stress, okay? That's the stress. However, there is a constant in here we need to solve. Okay? All right? So what's the boundary condition we can look for in this problem so that we can solve for that constant C3? Do we know the stresses? There are two boundaries, right? R equal to 0 and R equal to capital R. Okay? Do we know the stresses at R equal to 0 or at R equal to capital R, or simply, that's often simply said on the wall, on the tube wall or the blood vessel wall. Okay? Do we know the stress at these two locations? We don't. Okay? So by looking at the problem, the stress is not given, so we don't know what the stress is. However, we do know that the stress at the center or at R equal to 0 should be what? Should be a finite number, okay? Shouldn't be infinity. So that means what? C3 has to be 0. Because if C3 is not 0, as you can see, at R equals 0, the stress will what? Will be infinity. Okay? And of course, we don't expect that to happen. We know that's not the fact. Okay? All right? So basically, C3, sorry. So of course, from here, you know, at R equal to 0, and tau RZ is also 0. Okay? And we can also sort of use this as a boundary condition. Okay? To use that, well, how do we know at R equal to 0 the shear stress tau RZ has to be 0? You can get that by looking at the symmetry of this problem. Okay, so basically at the center, and that's where the symmetry is, axis symmetry, right? So that's the axis of symmetry for this problem. And there, stress should be 0, because if it's not 0, what? If it's not 0, and then you go from one side to the other, okay? And you will get, say you have a stress when you go from one side to the center. The other one should be better. So you, because of the axis symmetry, if tau RZ is not 0, okay? And you can imagine, you go gradually from here to the center, you get a tau RZ, right? And then you go from this side, you get another, and you'll find out that these two should be opposite of each other. Of course, they should be the same. Of course, opposite, the same, that means has to be 0, okay? So if you want to use this as a boundary condition, you know this can come from the axis symmetry of the problem to get tau RZ equal to 0. And there's another way to get this. That's to look at the calculation of tau RZ right here. So basically, this is the velocity gradient we're looking at, dvz dr, okay? You can see if tau RZ is not 0 at 0, at r equals 0, you will have what? A velocity gradient at the center. If you have a velocity gradient at the center, so that means what? The velocity profile is not smooth. You get something like this, right? The velocity profile at the center, at r equals 0. It's pointed in. It's not smooth, okay? So, of course, again, this is not physical. Because of that, you have to have tau rz or the velocity gradient equal to 0. Anyway, different ways, but same conclusion. So C3 is 0, tau rz is 1, whatever that's left. So that's the shear stress, okay? So once we have this, of course, we can try to look at where the shear stress is the smallest and largest, right? So where the shear stress is the smallest? Center, right? B. So obviously on the wall, it's going to be the largest. So on the wall, the shear stress is typically written as tau W on the wall. So RZ at R equal to capital R. So that is P0, PL, R, and L. All right, so once we know this, of course, we can calculate everything that we've calculated in the falling film problem, okay? So, and there we calculate the force applied by the fluid to the wall. Of course, here we can do the same thing. So then the force exerted by the fluid on the whole wall Fz, it's simply what? Stress, which is a constant, times the area. Area, that's 2 pi r L times W. So we have 2 pi r L times that, 2L cancels, so pi r squared. And of course, we can plug in the capital P0 and L. You'll find out that this number here is simply this. So the force applied by the fluid to the wall is simply what? See, the pressure difference times the cross-sectional area plus the gravity of the fluid. This shows what? Mechanical equilibrium, okay? So that means, see, this is the force basically applied on the fluid too, okay? All right, so the pressure at two ends, the gravity, right? So if this is the force exerted by the fluid to the wall, that means the wall also applies the same force to the fluid, right? So they balance each other, okay? Okay? And what's the direction of this force? The force applied by the fluid to the wall. Up or down? Down, right? Because the fluid is flowing down, of course, it's going to try to drag the wall with it. But of course, the wall is not moving. That's because, that's why there's its force, right? Okay? And also, if you look at the direction of the stress, tau RZ on the wall, you'll have the same conclusion, okay? So that's wall, okay? You're looking at tau RZ, right? Normal direction of the surface in the negative R direction, right? So of course tau RZ is there, okay? So there we go, all right? When you look at the wall, the normal direction of the surface of wall is pointing to the negative y direction. Okay. So, all right. So that's that. And what else did we do? Well, we also looked at the velocity, right? How can we get to the velocity? Again, what relates the stress and the velocity together? Newton's law, right? For a Newtonian fluid, tau RZ is negative this. This is from here, okay? See, tau RZ is equal to negative mu, this. But this one is 0, right? So you will have this loop to the left. Newton's law relates the stress and velocity together. So of course we know what the stress is. It's equal to 2L and O. So another differential equation, okay? How do you solve it? This one's easy. You divide both sides by negative mu, and then the solution, okay? So negative mu, you integrate, you have 4L, mu L, sorry, mu L R squared plus another constant, C4, right? If you find this difficult to understand, then you need to review the DFQ, okay? So how do we determine this constant? Boundary conditions. Do we know any velocity at any boundary? On the wall, right? There the velocity should be 0. The wall is not moving. So on the wall, I don't know whether, I think I mentioned it. I forgot whether I wrote this. This is typically called, or commonly called, the no-slip boundary condition, okay? Which means, again, the molecules of the fluid and the molecules of the wall, they adhere to each other strong enough so that there's no slip. There's no slippage between these two, okay? So same velocities, okay? Velocity equals 0, of course. You plug this in, you can determine C4, right? So kappa R squared, 0, plus C4. Okay, so you can get C4 and plug it back in to get the velocity. So once you've done that, you find out the velocity will have this expression. So we factor some stuff out. Okay, and then this is the velocity profile for the tube flow. Like the volume flow, this is also what? Parabolic, okay? So R squared, there's X squared, okay? So of course, where the velocity is the largest? R equals 0, right? Obviously, the larger R is, the smaller the whole thing is, right? So when R is equal to 0, that's the maximum, which is what? Everything that's outside. That's the maximum velocity. So this is equal to velocity maximum 1 minus R over R squared. Okay? So this is called the Huygens Hassuye velocity profile. Huygens is German, Hassuye is French. So they apparently did studied the tube flow independently by experiments. So that's why it's named. Of course, back then, you know, scientific communication was hard, difficult. So they didn't know, of course. Anyway, that's why it's named after these people. And also from here, you can see why the unit for the viscosity in the CGS unit system is named poise. That's from here, okay? First part of viscosity, poise, okay? Of course, you know, the whole name is Pasouillet. That's French. I used to pronounce it as Poiseville. Obviously, that's the English way of saying it. Okay. All right. So, what does it look like? It's parabolic. So let me just draw this and let you go. So it's a tube, right? Velocity largest at the center, and smallest on wall. So this is the velocity profile, the sketch. So the velocity profile can be used to refer to the equation that's there, and can be also used to refer the shape of the velocity. So that's that. And of course, this is where the maximal velocity is. And on the wall, that's where the largest shear stress is, tau W. Okay? Now, by saying that, the velocity profile has to be smooth, has to be smooth, and that means, see, has to be something like this, okay? It cannot be pointed at the center, okay? So, and that's it for today. So there's something else we need to talk about next time, but not much, okay?